Now that we have an understanding of the physics of how electronics work, what we're after, what we're chasing, what we're trying to do, now we're going to start diving into how and what does these values mean and what are they doing. Okay, so this is getting deep into the meat and potatoes of it. So one of the things that we're going to look at is how do I know what I'm looking for, which is what we're going to talk about with Ohm's Law. And then afterwards, we're going to talk about how do I depict this type of stuff in a schematic so that I can represent it with a picture instead of having to write out a bunch of words. So let's start in on the basics. So what is Ohm's Law? Ohm's Law, is the governing law behind electricity. It's the law. It's what happens. It's what it is. There's no way getting around to this. Ohm's Law is going to work all the time, every time. That's why it's a law, not a theory. Okay? And we will use this to solve basically everything from here on out is using this Ohm's Law. So where did it come from? This came from George Simon Ohm. Okay, for reference, he was born 1787. Okay, long time ago. He was a college professor, kind of like me. Except for not like me, this guy knew a lot more stuff than I do. He was really smart. So he was a college professor in 1817. So he was in his 30s when he was a professor. In 1827, George published his first theory about electronics. So this was the first theory of electronics. And in that theory that he presented, he said, this is how electrons work, because they knew about electrons, they knew what they were. This is how electrons work, this is how voltage is, this is all current, this is kind of stuff like that. Here is my ideas. When he presented this idea, he was laughed out of academia. He was literally chased out from teaching because of the backlash to his theory. People did not want to understand it. People didn't understand it. They thought he was crazy, and so he was chased out of the academic world because of that, which was kind of tough. So what he was doing in his experiments and what he discovered was that he would have a coil of wire. So we had this wire, this cable sitting here, and it would come around and it'd be wrapped around this giant spool, many times. And then he wrapped around there. I know it's a very poor picture of a spool of wire. Let's see if I can grab a better one. Spool of wire. Oh, there we go. That will work. Copy that. All right, here is my image of a spool of wire. So that's basically what he was doing. He's doing these experiments with the spool of wire. So what would happen is he would measure the resistance of this wire. So he found out that for every 1,000 feet, or he would get a couple hundred ohms, or he'd get some value of resistance. He would be able to measure how much slower the current was versus at the end of the loop of wire, spool of wire, versus it was at the very beginning of the wire. And so we found out that the longer and longer you made this wire, so we had this length. So as length went up, the resistance also went up, meaning the more material you had in play, the more resistance. And he found that as resistance went up, current went down. So he started to map this out and realize, hey, this is happening every single time I do this. I can then use these two values, a resistance and a current. I can determine the length of the wire. Well, guess what? That's how they do it, or that's one of the things they do for measurements when they're tracing wires that are broken. They measure the resistance, and based on the resistance of it, they can figure out how long it is versus how long it should be. Now, there's other ways of doing this, but this is one way to determine that. So he found this idea, and he found that as the length went up, resistance went up, and because of that resistance going up, the current would go down. So what happened is, as he continued to work on this, he went and worked on this more and more, and he went through different aspects. He finally published some more material. In 1841, this is where he published his book. And this was the entire theory of electronics. This book and these theories that he published, this eventually became Ohm's Law. When academia finally realized that he wasn't full of crap and that he actually knew what he was talking about, this is what then became Ohm's Law. All right, so what is Ohm's Law, and then how does this apply to me? Well, Ohm's Law is quite literally just the relationship of how electronics work together. So what we're looking at is the relationships he found Okay, this is what he found. As a voltage increases, the associated current also increases. If resistance increases, current drops. And as the resistance increases, the voltage drop, so basically of that component or the section he's testing, so the voltage drop of the component increases compared to the rest of it. So if we're looking at multiple spools of wire, if one spool of wire has 1,000 feet of it on it, another one has 500 feet of it, and you connect them up together, you run a current through it, the voltage drops of each individual spool of wire are going to follow this relationship. Whichever one has the most resistance or the most material is going to have a bigger portion of the voltage drop across it, matching up with what we know about the physics of electricity. The more resistance we have, the less current, which means the more force is going to be required to push those electrons through at the rate that we want. So they all go hand in hand with the physics of what's going on. Mathematically, this is what it looks like. So mathematically, this is our formulas. Voltage over current and resistance. So here's Ohm's law in a mathematical nutshell. And one of the things we have is we can use this and draw it to references of what do I need to solve for when I'm looking for things. And the way we do this is we look at our value. If I want to know what the voltage is, okay, I'm going to take this, I'm going to cover up voltage. If I cover up voltage, what do I have left? I have a current times my resistance. Okay, see how it's lined up? When they're right next to each other, we're going to multiply them. When they're underneath each other, we're going to divide them. So now I've got voltage. Let's say I wanted to solve for current. So I cover up my current. My current is then going to be equal to my voltage divided by resistance. And then if I want to know my resistance, I'm going to cover up the resistance. My resistance is equal to what's left is voltage over current. So here are my now three formulas for solving anything in Ohm's law. Voltage, current, or resistance. We cover up one of them, take whatever's left in their physical relationships. So then, after Ohm came out with these ideas and after these became accepted, we had some more work that came in. So here we have Ohm's law. And what we did is watt was another professor. He came along and he discovered Watt's law. So built upon Ohm's law and came up with this. What Watt's law did is he found it as a proportion of power compared to its voltage and resistance, or sorry, voltage and current. So Watt's law states power is over voltage times current. And so then we could then use this to find a fourth aspect. So now this gives us voltage, current, and resistance. Watt's law is now the relationships between power, voltage, and current. So same process. If I want to solve for power, I just simply take voltage times current. If I want to solve for a voltage, I take my power divided by current. And if I want to solve a current, I take power divided by voltage. Now, the cool thing about this is this builds upon Ohm's law and Watt's law. So they work together. So we can intermix these guys. We could go through and then solve for power based on current and resistance. So if we looked at that, for example, I want to know what power was, but let's say I don't have my voltage. I have current and I have resistance. Well, I can substitute this voltage for this formula. So I take my I times R. Actually, I'm getting ahead of myself. Let's go. Power is voltage times current. I'm given current and resistance. So I still want to solve for this power. So I can substitute this. So power is then equal to voltage. Voltage is equal to current times resistance. So there's my voltage. And then that times the rest of my formula is current. So I'm given current and I'm given resistance. So therefore I have power is current times resistance, or current squared times resistance. And now I have four options that I can use to describe anything that's going on with electronics: power, voltage, current, or resistance. And any combination of these I can use to solve for my values coming up. So what you're going to want to memorize is Ohm's law and Watt's law. You don't necessarily have to memorize all these little formulas because you can just solve for it. Voltage and current will give you resistance. Current and resistance will give you voltage. Voltage and current will give you power. And you can mix and match these as you need to as they come up. All right, so that is Ohm's law. That is what we're looking for the basics of this. Everything we're going to do is going to be based off of these two laws. Now, one of the other options that we're going to be looking at and things that we're going to do is we are going to be after how do these things work and how do these look like in a circuit. So what we're going to do is I'm going to pull this up because I don't want to draw them all. So give me just a second and I will pull this up. There we go. There is my documentation. Nope, I don't want that one. I want this one so I can grab the chart and just move it over. Let's see. There's that. There's the resistance. There we go. This guy. So how do I reference? Uh-oh, I didn't transfer. That mostly transferred over. Yeah, I'll fix it here in a second. So how is this going to translate to schematic symbols? So how do I represent all of this information in a circuit? Because again, we want to try to find simple ways to do it. So a schematic is a way to describe information or a circuit in a picture than just with a bunch of words. So what I would have is a very basic circuit is going to look like this. And this is going to mean something. So what I have to do is look at all the different symbols and see what they represent. A resistor looks like this. So this guy is the same schematic, so this is a resistor. This is supposed to be a DC supply, but it didn't copy over perfectly. So a DC supply is going to look like this. Okay, this is a positive, this is a negative terminal. These are usually what we refer to as batteries. When you have multiple sets of these, so like a positive and negative pair, this is kind of as a default, this represents cells, or like in this case, a 2-cell battery or 2 batteries connected together. I just generally use them with the 2 to identify what's going on. Reference ground this is a point that I'm going to say, I want you to take a measurement based on this point right here. Signal ground is where I'm going to come in and say, this signal is in relation to this point. Now, a ground and a ground are the exact same thing, but they have different meanings when you're used multiple times. So that means this is a ground, this is a ground. This is where I want you to take the ground for the reference point, but this is what my signal is looking at as ground. They do mean the exact same thing. They are a common point. But if they're different symbols, then they are not the same point as far as it comes with values that we're looking at. This is earth ground. This is where you're connected to in the outside, your grounding port in your plug. So when you have your plug that looks like this, come on, go away. That right there, that is your earth ground. That goes into a rod that's buried 6 feet in the ground. Your next one that we're going to see is a ceramic capacitor. So it's going to be looking like this because it's 2 pieces of metal with an insulator inside. An electrolytic capacitor has a curved side and a flat side. So a ceramic capacitor, there's no polarity. It doesn't matter. The electrolytic, when you have this curve, this is your negative side. This is your positive side. That does matter. The symbol for an inductor is a curly Q line. It's a coil of wires that are put together. We have a diode, triangle with a flat point. This is going to be showing directionality. This flat right here, this is your negative side, this is your positive side. A Zener diode is going to look just slightly different. The only difference is this little flat. This is still your negative, this is still your positive, but we have a Zener diode. This one is going to regulate to a specific voltage. This is a Schottky diode, so we have kind of the symbol for an S. This is going to be a high-speed diode. A light-emitting diode are the most common, LEDs. That's what it stands for, light-emitting diode. You flow a current through this diode and it emits light, so we get that little symbol. A lamp is an incandescent lamp. It has a coil of wire in there, so it's basically an inductor, but that inductor is designed to emit light when a current runs through it. We have a current source. This means we are going to be spitting out a certain amount of current, and the voltage is going to be whatever it needs to be to maintain that current. A voltage meter is where measuring the voltage. Current meter is where measuring the current. Resistance meter means we're measuring the resistance. An output is just a pin with an open circle. A potentiometer is a variable resistor, so we're going to have the symbol for a resistor, and then this leg makes it variable because we're pointing to somewhere inside of that setup. Now we have to give some more information about this resistor, how much, or potentiometer, how much are we splitting it up between these 2 points and things like that. A rheostat is a potentiometer where we short out half of it. And we're going to talk about all these later, so don't worry and feel like you have to know them now. So we short out or get rid of a certain amount of the values. The other things that we have is we have transistors. We have 2 different styles. An NPN has the arrow pointing down away from this center point, and we have a PNP which has it pointing to the center point. And those are just differentiations of the amount of current and the direction of current that they have going to control them. We have a MOSFET, which is broken up by a bunch of lines. We have a relay, which is a coil, basically a capacitor, a separating block, and a switch. This one's kind of hard to see, so I'm going to redraw it. So a relay is we have a coil, and then we have the core of whatever that coil is. And then what that's going to be attached to is a series of connections. So we've got a connection here. We have a connection here. And then we have another arm that's going to have a connection either to there or to there. And this side is usually attached with another spring. So what's going to happen is this spring is going to pull this connection down and pull it to one side. So we run a signal through here. This builds up a magnetic field. It pulls a signal, or the spring pulls it to one side. And then when we get a big enough magnetic field, it pushes it over to the other connection. So this is kind of our quick little schematic symbol. You will see them drawn somewhat different in different books. There's no real one standard idea for a relay depending on how it goes. But this is the idea, is we have a coil that controls a spring-pulled connection point mechanically. We have a fuse. This is a fuse is designed to interrupt current. If we get too much current flowing through it, it actually breaks apart and creates a spot where no current can then flow through those two connection points. A circuit breaker is going to be a symbol that we use, and that's a resettable fuse. When too much current happens in the circuit breaker, this thing basically pops up and disengages. We have to put it back into position. And then the last schematic we're going to talk about is an AC signal. So we have our circle going in and out, but inside we use a sine wave to designate that it is an AC signal versus a DC signal. So the difference between this, DC is direct current, or one-way current. Okay, so one-way current or direct current. AC stands for alternating current. Multidirectional. Or another word is always changing. Okay, it's not staying at one value. So direct current always stays at one value. AC is going to be changing. That's the biggest difference to remember. All right, I know we covered those pretty fast, but again, these are what we're going to use for the names and things like that. And then as we get going, you'll see more and more where these come into play, and you'll see how these come into play. So just be aware of these. We're going to go through them. You're going to see them more often, but just notice that's what the symbols are standing for when we talk about them. All right, last thing that we're going to talk about is kind of an example of how to use all these things together. One of the cool things that we have is this idea of ratings. How much power, how much voltage, how much current can a battery supply? So if I have my normal batteries running around, so I'll go batteries, and I'm just still in an image because that's what's fun to do. That one's kind of blurry. Yeah, sure, why not? Copy, paste. All right, so here's some batteries. Okay, that's what they're going to look like. So each of these batteries has a certain amount of power that it can give until the chemical reaction inside or the stored voltage or whatever it may be, until that dies off and it can no longer supply it. So what these are is batteries have a rating called milliamp hours. So if you look on the side of the battery, it should give you a milliamp hours. If not, you can Google it and find out what they are based on the brand of the battery. And this is what basically, it can supply a certain amount of current for a certain amount of time at its rated voltage. So if we look at a battery, so a Duracell battery, we have a couple of them laying right there. So a Duracell battery has a voltage of 1.5 volts per battery. A AA battery, kind of the standard ones, is rated from the company to be able to supply 2850 milliamp hours. So that means this one AA battery could supply 2.85 amps for 1 hour, or 2,850 milliamps for 1 hour at this 1.5 volt rating. Okay, to give you in comparison, a D cell battery, which I think this guy is the D, this one is a C battery, and then this one is your AAA. And then this is just what they call a 9 volt battery. Okay, so your AA battery right here has 1.5 volts. Your D cell battery also has 1.5 volts, but its current, it can supply 15,000 milliamp hours, or can supply 15 amps for 1 hour. So not a lot, and then it's depleted and it goes away, and then that 1.5 volts is no longer there. But that voltage is also going to be slipping down a little bit as well as time goes on. So we can go through and then use these and figure out exactly what I'm after or how long something's going to work. So what I can come up with is if I have a flashlight. All right, there's my flashlight, there's my switch, here's the head of my light, and what this is going to do is I'm going to put 2 D cell batteries in my flashlight, and my lamp that's up here is connected like this, and then we have a wire that goes to one side of our switch. This part of our switch, go away, comes up to here, and that's then going to connect into here on the negative portion. We got a positive, negative, positive, and that's going to connect here. So my switch, when it turns on and connects this circuit, it's going to allow my light to turn on for a little bit of time, depending on what my rating is. So these guys have a rating of 15,000 milliamp hours at 1.5 volts. Now, when we are connecting these together, each battery is going to be putting out that much current, but when one of them dies out, the other one dies out too, because we're going to lose this voltage. This lamp is rated at 3 volts at 0.30 amps, meaning this lamp requires 3 volts, which is why we have these 2 D batteries. 1.5 plus 1.5 gives me the 3 volts, and it needs this 0.3 amp or 300 milliamps to be able to emit light. We still will have current flowing through it when it drops down farther, but it won't be producing any light anymore. So what happens is, based on these ratings that we have, how long is this flashlight going to last? If it requires 300 milliamps for 3 volts, so the 3 volts is satisfied, we need to know how this 1500 milliamps is going to be split up. So I take my 15,000, not 1500, milliamp hours, divided by the usage of 300 milliamps, which, remember, the current is just simply the number of electrons that are moving past a point per second. So this can produce 15,000 milliamps worth of electrons moving through the circuit for 1 hour. We want 300 milli per second. So what we end up with is these are going to come out, the milliamps are going to cancel, and we're left with hours on top. 15,000 divided by 300. This is going to give me 50 hours of operation. And that's allowing the current to flow at those voltages. Now with these batteries, they don't always stay at 3 volts. They spend a lot of their current, they lose the voltage. When we lose the voltage and the current, we don't have enough power, and so it's still going to be using it, but we are just not going to be seeing the light as it goes through. So that's one of the cool things that we can solve just based off of these values. So a really quick way of looking and using our voltage and our current and our resistance and all that kind of stuff in a very, very basic circuit I can then determine how long my batteries are going to last based on how heavy I'm going to be using them.